My name is Zhiqi Tao. I work for Intel. I'm a system engineer in the Lustre team. So my job is to help partner customer design the Lustre-based storage system. We all know Lustre itself is a file system, so most of the times we will need some hardware, right, to run Lustre. So here I present a generic methodology, right, to analyzing performance bottleneck on a storage system. You note here, I do not specify just for Lustre, right? Because I think this is a generic methodology we could apply to other platforms as well. But when I present the case study, I will still use Lustre because that's something I'm familiar with. So a storage system could be pretty complicated, right? So we have a disk, we have network, we have a storage controller, right? When we have so many pieces in one box, especially when we try to troubleshoot the performance bottleneck, we can easily get into the Bart Simpson defense case. For example, first of all, it wasn't me. Second, I didn't do that. Thirdly, you cannot prove I did that, right? So when we run into this kind of finger-pointing situation, we really need to have data to support ourselves. So that's why it's important we collect enough information. But sometimes, especially for the complex system, it's really hard for one person to have a knowledge of the entire stack, right? So what I'm presenting here is, personally myself, I don't consider myself I'm an expert for everything. I only know some of Lustre and some of hardware knowledge about hardware storage system. So this kind of methodology, what I used when I analyze the performance bottleneck. So by no means it's a best practice, it's just experience sharing. I hope it be useful for someone else who are also interested in this topic. Lastly, I'm open to your suggestion, right? So I'm hoping you can tell me Zhiqi, you're stupid, we have better idea on this, right? Feel free, seriously, yes. I always amazed how much I learn when I present or teach a class, right? So there are always some much smarter people in the world can do that better job than me. So I have a service, some instruction, and I'll present a general storage system. We need to have some context, right? What I'm talking about here. Then talk about the performance, why we think performance is important, and some methodology. And I'll present a case study, and then conclude, right, the talk. So first of all, as you can see, this pyramid, right? So a storage system can really be complicated. We have disk, storage controller, network, HPA on the server, and the server itself, and some of a network interface, and finally, client, right? If you're a customer, most of the times you only come see the performance all the way down, all the way here, right? You have no idea what's inside the box, especially if it is not open platform, right? So when we design a storage system, there are many considerations. For example, compatibility, performance, reliability, scalability, all these things. And most importantly, most of the cases will be cost, right? So how do I design a system which will be cost-effective and also meet my requirement, right? So when we come down to the storage system, we often ask two questions. I often got this kind of question: how to improve the performance of a storage system, and what's the bottleneck? When I got this question, normally I turn the question around. So what do you expect, right? So we need to set the realistic expectations, right? And so that's why, we, sorry, I'll jump ahead a bit, right? So when I'm showing the situation, I'm sharing the terminology, methodology I talk about. So when I got this two kind of question, normally I turn the question around, so how efficient your file system is, what do you expect? We need to set a realistic expectations, right? There are some cases we get is, oh, this is too good to be true. And sometimes that comes with some consequence, right? For example, for some of storage controller, if we do not turn on the cache mirroring, you'll find that the performance is really, really good. However, if you happen to have the bad luck, one of storage controller had a crash, and you lose some data in the cache, right? So that's kind of a case, too good to be true may not be the best. And I want to say, because I work on Lustre, a well-designed Lustre file system can achieve 90% of underlying hardware bandwidth. So if you're interested, contact me after a talk. Right? That's what I do. So performance is normally the most noticeable measurement, right? As a system administrator, most of the times you got the call from one of the users say, why I get these little waiting icons, right? Keep spinning, right? So there are some good reasons behind this, right? I/O module, even today, commonly to be the slowest component in the entire computing system. We have a much faster CPU, we have very fast RAMs, right? However, unless we could destage the data to the storage, we will not be able to release CPU cycles, which is why sometimes when you see a lot of I/O wait, that's often indicate malfunction in the file system, the file storage system, right? So high performance is difficult, right? And it's also difficult to be cost effective, especially, and achieving high efficiency will be even harder, right? So for example, what I'm trying to say here is, if we compare two systems, one gave me one rack, I got 10 rack, I got 10 gigabyte. The other one rack, I got 2 gigabyte. Compare these two systems, obviously the second one is more efficient, right? So how to design a high efficiency file system is what I do, and what our team does, right? So if you contact Intel High Performance Data Division, we have a team to look after you. So they not often require years of experience to architect a system, but there's a methodology we can follow, right? Especially if you're using open technology, right? You have some control, right? What I mean here is there's a white paper you can download from onecloud.com, right? This is the white paper I wrote with a couple of colleagues last year. And so this is a generic methodology, how we choose proper hardware, right? And to design our high-performance storage system. So when we see a bottleneck, right? So sometimes even a well-designed system, we still see some bottleneck. It is not uncommon. So what could be the cause, right? That could be multiple reasons. For example, could be some factor we did not consider when we design the system. Could be hardware are not as good as they claim to be, and could be bad luck, right? For example, we just happen to have a bad wrong, I would say like a bad batch, right? A faulty batch. I got into this situation a couple of years ago when the files, I noticed that some of these are just much slower than others, right? There could be some limitation in software, right? For example, the metadata performance before Lustre 2.3 was not as good as after 2.3, right? And that's another reason you want to try a new one, right? And could be like some tunable we need, right? Especially, software itself generally built in some default parameter. Those parameters might not suit for everyone, right? If we can make so for example, take Lustre as an example. If I download Lustre and I can run it in a small VMs, and you wouldn't expect that same kind of Lustre without any tunable would work the best with much bigger box. So troubleshooting performance, bottleneck, that's part of my jobs. And once again, right, I promise this is the last one, right? Contact us and we can look after you. Or, I talk about my methodology here. So when we have this performance bottlenecks, there are generally two types of approach, right? So to analyze a complicated system, top-down or bottom-up, right? So eventually, we need to find out where the bottleneck is. So if we take a top-down approach, basically that means you need to trace down the problem, right? It's like peel the onion, or even worse, look for a rabbit in the forest, right? Really, really hard, especially. I admire some people have this kind of skill, like they can use D-trace system and to tell you exactly which the process is taking all the system resource and which data structure is not efficient to handle concurrent request. Those kind of cases, I admire those people can do that. But often they require either special tools, right, and also in-depth knowledge. Right, so and certainly that's part of my motivation is really hard to generalize the result, right? I can identify the issue in a particular system. Would that results be generalizable? I don't know, right? And also it's kind of time consuming because normally it's kind of reactive actions after we identify, we have already seen some issues, right? In these cases, most of the time, it's very difficult to make any change, right? Especially when you have the system, the storage system in production already, right? Once you build it, you just some of this analyze is destructive. That means you need to tear things down, and that's just not efficient. And lastly, fingerprinting, like I mentioned, right? I didn't do that, it's not me, and you cannot prove I did that, right? The bottom approach, basically equivalent difficult, right? You have still need, even though you analyze from the backend disk, you still need to identify which one it is, right? So can also be very time consuming, right? So my motivation is I want to propose a methodology. It's proactive, not reactive, right? So we take steady steps before we encounter the story like performance bottleneck, right? And we do not rush to the end. And debugging from there, we build a storage system step by step, right? And also I want to use open, general available tools, right? So we can easily compare the system, right? Especially, I like to design the efficient system, not just absolute number, right? I want to show I architect the system even pretty small, but we got a very nice performance, 90% system utilization, right? And I think that's much more interesting than just get pile up hardware together and get one of absolute numbers. Sometimes you are just in luck to have someone willing to pay for to get that. And also, we want to be able to narrow down the scope of bottlenecks, right? So, because personally, I'm not an expert for, for everything, and I have to consult the subject matter expert for that to do the in-depth troubleshooting. But before I do that, I need to have the proof, I know this is the scenario, right? So in order to do that, firstly, I'd like to talk about how do we see the storage system from a different analogy, right? So we saw the diagrams using the pyramid, right? But personally, I don't think that's the best way. What I see the storage system is really a pipeline, right? So the data flows from backend disk to front-end client, or client writes something, the data flow all the way back. So it's a pipeline. So why pipeline is better analogy? What I'm saying is, pipeline means the slowest point decided the throughput of entire system. So it doesn't matter you have how much disk in the backend, or it doesn't matter how powerful your server is, because your bottleneck, if you have a slow network, you wouldn't see that anyway, right? So that's why when we identify bottlenecks, we identify one of a component in the entire So in order to do that, we need to understand the specification of each component, and also we need to understand the overhead. For example, we might have lots of very fast disk. Let's say you have a 15K disk in a storage controller, but the storage controller is in a storage disk, but the controller itself only give you very narrow bandwidth, or you only have one SAS link out, right? So that's not sufficient. So you can see this line here, right? So if we can, the flatter this line is, the more efficient this storage system is. So what I'm interested in is I want to make this line as flat as possible. So that means most of the bandwidth I have in the backend will be visible to my client. Or what a client want to write, that would see the backend disk. So let's try this kind of methodology on something I'm familiar with. Right? So this is a generic Lustre storage system. Right? We have a client, and client normally we have some computing client on the high-speed network, InfiniBand or 10 gig. We can also set up a Lustre router to route the traffic from a fast network to like a gigabit Ethernet, right? Sometimes we have a scientist, they have some desktop, right? They want to fetch data from a Lustre file system, right? We have Lustre router, and we have a metadata in the middle, and we have object storage data, right? So this can be a pretty complicated system, right? So how do we, and of most cases, where we start, right? Personally, I prefer start from the back end. Let's just talk about the bandwidth for this example, right? So even the backend storage system, we could have this kind of like 60-disk enclosure, right? The two systems, you can either see the system or the box in the back, right? They both have a 6 disk in one enclosure for your footprint. And they connect to some sort of a controller, right? The controller would have a cache mirror link between them, just to make sure like if one controller failed, the other controller can take over the I/O transaction. Then we use some sort of like a storage area network, like either SAS, fiber channel, SCSI, or SRP connect to the Lustre OSS. When Lustre generally require, we design the read, right? Because Lustre has no knowledge about anything beyond the file system, right? And it's basically long. So let's take example. Let's take the example, right? So for example, I configure 10 disk in RAID 6, right? And that way, right, I can tolerate 2 disk failures. However, you can see I have a 60 disk in one box. Normally we have let's say we have a InfiniBand out. Would that be sufficient? One disk would give us, one SATA disk, like one SAS disk, right, 70 to 100 RPM drive would give us 150 megabytes per second. So if I configure RAID 10 or RAID 6 here, 10 disk, and I have an 8 data disk and 2 parity, right? And most likely, this would give me much higher bandwidth than the French network can accommodate, right? So we need to identify if that's true. That's the truth. So generally, I will start with benchmark in each individual OS in the RAID group, just to make sure like we have a homogeneous performance. So for example, if some of the RAID group significantly slower than others, that generally indicates some disks are not performing well, right? And there are some statistics. If you see like a slow disk, generally they indicate that disk might fail. They're still okay now, but it might fail like in, let's say, 1 month or 2, right? So we benchmark individual ones, and then we benchmark all of them, see where the bottleneck is. Can we do something, right? So for example, we have 2 link out here. If the aggregated bandwidth of all of the RAID group exceed 1 data link, that means we could connect this we could connect these two controllers to one OSS node because that's already sufficient, right? Otherwise, if all of them do not exceed one of them, there's no point to connect to two OSS node because you're going to be this is going to be a bottleneck anyway. The things we need to pay attention is because Lustre has no knowledge or control on the backend storage, right? So we need to make sure we have a proper cache configured. So for example, if there are some hidden cache, we need to turn it off, right? We have to, for example, we have this cache mirror link, and we need to battery backup cache on storage. And if we have a cache on HBA, some of the fabrication HBA has cache, turn it off because Lustre has the knowledge on it, right? And I believe the same thing for other file system too, right? But another thing to keep in mind is sometimes by turning off the cache, we might get better performance, right? And so having cache on might not be good for everything, depends on the controller. To analyze the backend storage, and we have some toolset. For example, VGBench, the VDBench, I have a lot of respect on it. It's basically switch army knife. You can do pretty much everything with it, right? So, open source, it's a free downloadable from SourceForge. With Lustre, we shipped the SGPT survey. We can test, from under different concurrent region and different thread, right? Normally, the size in order to avoid the caching effect, or make sure cache is not in a place, right? So we request twice of system RAMs. That way, I know there's no caching, right? You can go to that Lustre operation manual and 24.2 see how to do that. And many people use the DD, and this DD is good, for simple thing, but not good for analyzing the storage I/O primarily because DD do not support multi-thread, right? So if we only have a single thread, we got some number. That not means we will get multiple number by increasing number of thread, right? So what we want to find out here is the entire storage box. What kind of performance we can get out of it. And another example I want to show here is if we compare these two configurations, right? You can see this one only have two. Each controller pair with one, this 63 enclosure, and the other has several of them, right? They can just data the chain. So these two systems efficiently just give us same performance, right? They have different capacity, but same performance. So if efficiency is all we are after, and we need to consider, which one is good enough, right? So how many OSD is best fit for one OSS server, right? So this kind of the case, and we want to use this OBD filter survey, right? For other file system, you might have you might use other tools, but with Lustre, we can use their survey to simulate Lustre workload, right? We can simulate how many concurrent thread we want to have. We can simulate how many objects we want to write simultaneously. So that way, that will tell us, if we have 2 OSD and 3 OSD give us same performance, that probably means that 3 OSD be overkill. We want to go back one step, right? We need to configure more OSS node here. Go ahead.
So does that sustain? I mean, it kind of could sustain its server per controller. I mean, if you have 2 servers connected to a controller, to believe that will sustain it. I mean, any bandwidth could be delivered by the controller.
Yeah,
I could go for a really high number of threads and objects and just try to stay. Or will expect that will not give me the peak of the results from the controller.
Different controller will give you different result. Some controller, you will see you have this path, then when we increase the number of threads, we can support up to 256 threads, and I think it's even higher. We can tunable, but most of the controller they would not be able to have higher performance after 256, right? So when you get there, it stays, right? But some of controller, they are not that good. When they reach the top, they actually drops after it will continue to increase. So that's why we need to try different combination of a thread. Right? Because number of concurrent thread on Lustre server is also tunable we can play with. This is called the max OSS thread. And so if we know we can accommodate more thread, we can try something there as well. Yeah. So after, I should keep referring to that these diagrams, I guess. That will give us, this diagram, right? So we talk about the controller, we talk about the server, and now we need to talk about the cluster network, right? Because regardless what we benchmark, what we got from the backend, right? If the front-end cluster network is our bottleneck, we will not be able to make those bandwidths visible from client. So one of the situation we might run into is like whether we have some blocking in the InfiniBand fabric or 10G fabric, right? So that's generally the case, right? For example, let's say we have a 32-port InfiniBand switch, right? So if we want to, most of the times we have more system connect to the one InfiniBand switch anyway, right? So that's case like if we have a 24-port on one side, another 24-port on the other side, if the node on connect to different IB switch need to talk to each other, we only have a half of the bandwidth. So that could be the bottleneck, right? And a better like this non-subscribe oversubscribable the InfiniBand fabric will be like 18 here. So that, but obviously this one is more expensive, right? So would this be enough for us? Sometimes it is, right? So the way to find out whether this network is our bottleneck is we need to run some tests. So for example, on the fundamental IP device, we might want to use like this IP write bandwidth, IP read bandwidth shift within the proof of test RPMs. With Lustre, we could also use LNet SelfTest. This one, not only we can test one-to-one, one-to-many, we can also test many-to-many, right? So I detected some issue in the past. For example, some of switch, right? If you test individual port, you get full bandwidth. However, if you have every port populated, you'll find you only have half of bandwidth, and something wrong inside the switch, right? So with LNet self-test, we could have multiple to multiple, right? And I don't think there's any like limitation there, right? You can specify size, you can specify the number of requests simultaneously, and we can specify different tests like block data or write, or we can specify this, like it's more like latency test, right? Small ping test, and whether you want to turn on the checksum or not, right? So that way we can really test the system and find out if the network is bottleneck. Another nice thing about this LNet self-test is because they only write or read data from RAMs, they will not change anything on the disk. So it's actually safe to test it, to run the test on production system. So lastly, client, right? So regardless of what we architecture or tried here, if client do not see the performance, and it's meaningless, right? So we need to, it's a performance matter on the client matters, right? So we need to run some test on the client side. And generally we use IO zone or IOR, right? So this supports different type of workload. Or lastly, right, probably most important, what kind of application you're going to run on this entire cluster, right? So you try that and see what kind of performance you get. So you can see we take steady steps, right? Every step we run some tests, we try different configuration, we understand the performance profile, right? From there, so if we identify some huge gap, right, say the like water flow things, right? If we see a big drop, it's better we stop there and analyze if that's drop make sense or not. Otherwise, and we're gonna hit the we're gonna be backed by this kind of issue in any way, right? So we can use as none of those tools I talk about here are proprietary, or you cannot get it, right? So everyone can download and feel free to use it, right? When we run those kind of tests, we want to look out for the system utilization and saturation. For example, if I have let's say I connect 30 OST, right, on one Lustre server, and I notice the CPU utilization is 100%, that's probably indicates the CPU is not powerful enough to handle that many OST, right? So those kind of information we need to collect as well, right? So you can use LStat, top, MPStat. These are generally available on pretty much every Linux distributions. Lastly, well, you can use we have this Intel Manager for Lustre. That one is kind of special, right? So we have all-in-one dashboard. You can see the CPU, RAM, or file system I/O, both metadata or read or write workload, right? You can get the aggregated logs, especially if in the cluster environment, right? The node report issue might not be the one actually causes the problem, right? So if we have aggregated logs and we can correlate event, then that would we had a better chance to and then identify the bottleneck, the performance issues, right? Also, we have a syntax highlighted alert, right? So not everything we need to pay attention on the logs, but if we see some red alert, that generally means we need to take some actions. All right, and that's all my presentation. Thank you very much. And you have any question?